Welcome to part 1 of our two-part Houdini tutorial from 9 Between, in which we'll be covering how to create this effect. Part 1 will cover the cube movement, so we'll just be creating some geometry for our cube. Once we've got that, we'll go ahead and throw on some color. Then once we have our color, we'll go ahead and shuffle our cube up, and then we can play it in reverse and clean up the edges and end up with a self-solving Rubik's Cube. Hope you enjoy. In Houdini, we can begin by dropping down a geometry node. We can just rename this node to cube, dive inside of this, delete the file node. Then we can drop down a box, and we'll be using this to generate some points. So change this to a polygon mesh, and then on its axis divisions, we'll just change this to 3 by 3 by 3. After that, we can drop down an add node. Plug your box into the first input of the add node, and then we'll be using this to delete geometry but keep the points. So if we activate that, we end up with this. We end up with a perfectly spaced grid that actually has the same number of points as cubes on a Rubik's Cube. So what we can do with this is copy some geometry to each point and end up with a Rubik's Cube. But before we do that, let's drop down a wrangle. Now, this wrangle will be generating some values. Those values will be the distance between each of these points, and we'll be using that a bit later. But it's good to have them now so that later on we can just make use of them. So we'll say at x max equals chf width, and then outside of the brackets divide that by 4. So we'll make a few of these, and I'll explain what they do afterwards. But just to explain this line, at xmax we're just initializing a global variable, and then we're assigning it a value, and this value is a channel float, so that'll be created when we create our spare parameters, and then we're dividing it by 4, and I'll explain why 4 in a second. So next we'll do at ymax, and that will equal channel float. Change this to height, divide that by 4, then we'll do z max, and once again channel float. This time we'll use depth, divided by 4. So now we can create these spare parameters, and then go to our box, and what we'll be doing is we'll be copying our size from each of these into each of our created parameters. So firstly we'll take the width, that'll be our x size. We'll paste it over here, say paste relative references, go back up, then we'll go over to our height, that'll be our y, go over here, say copy parameter, back down to our attribute wrangle. Once again, paste relative references. Finally we'll go up again, and on our z size, we'll say copy parameter, go to our attribute wrangle, paste relative references onto our depth. So what this does is it gives each of these points a value depending on the size of our box. So if we scale this up, these values will adjust. And the reason we're dividing by 4 is because what we're trying to do is we're trying to find the space between these points. So when we divide by 4, we're saying the height of 1 divided by 4 gives us 0.25. And 0.25 sits over there. So we end up with a value that is directly in the middle between these two rows of points. And it may not make much sense right now, but when we use it later you'll see exactly why that's important. So next thing that we can do is drop down a copy to points, and into our second input we'll copy this attribute triangle. So these are the points to copy to. We need a geometry to copy to these points. Let's drop down a box, Plug this into that first input, and you'll see we have a bunch of boxes that are overlapping. So what we'll be doing here is just changing its uniform scale down to 0.495. And what that does is it perfectly fits these boxes. And we end up with a slight gap in between, and so that'll do just fine. And so you can see we basically have a Rubik's Cube already. Now the one thing that this is missing is some color. So that's what we'll be doing next. So the next thing to do is drop down a bound. What a bound does is it creates a box around another geometry. So we have this geometry over here and each piece is separate, but when we drop a bound, it'll say what's the smallest possible box that we can fit around the object that we're feeding it. And so it'll create this box. Now what we can do with that box is color each side of these faces and then transfer that back onto our cubes. And to do that, we'll need a for each. So we'll do a for each primitive. And in here, we'll do a couple of things. So the first thing that we'll actually be doing is creating a meta import node. So on this for each begin, just click this create import metadata. And now we have this extra block begin. And this one, you can see, is calling in a few detail attributes. So what we'll do is we'll create an attribute wrangle next. In this attribute wrangle, we'll say float iter for iteration equals detail, open brackets, 1, comma, inverted commas, iteration. Close that off. And what we're saying here is create a variable called iter that finds the detail attribute from our first input. And first input, remember, is actually your second input. In Houdini and a lot of other programming languages, you start counting from 0. So input 1 is actually 0, input 2 is 1. So we're saying from input 2, find this detail attribute called iteration. Now we don't have anything in input 2. So we'll take this for each metadata and plug it in here. Now, if you remember correctly, we have detail attributes, and one of them is iteration. So what that does is, it gets the current iteration that we're working with. So every time this passes through an entire loop, we go to the next iteration. So once we're done doing this for the first phase, it moves on to the second phase. And so your iteration goes up. And you can see here that it's saying gather 6. And the reason for that is because we have 6 faces on our bounding box. And we're doing a for each loop to run over each primitive. So next we'll be doing a bunch of things in here. So we can just say Alt-E and bring up our string editor. We're doing a bit of vex, and it's more menial labor than anything really. It's not particularly complicated. So we'll just say if iter, which is our iteration variable, equals 0. Then do something. And what we'll be doing is setting our CD attribute. So at CD equals set 1, 1, 1. Now CD as a color attribute works with RGB. So when we say set 1, 1, 1, we're saying set a red value of 1, a green value of 1, and a blue value of 1. And when you have a 1 value in each of these positions, you end up with white. So what we're saying is, if iteration equals 0, then our color equals white. So we'll move on to the next one. We'll say if iter equals 1, then our CD attribute should equal another color. So at CD equals set. And in here, we'll choose a different color. This time we'll make it red. And red would be 1, 0, 0, because we have R value of 1, G value of 0, B value of 0. Keep doing this. If iter equals 2, do the following. This time we'll be saying at CD equals set. And for this one, we can choose a different color. We'll go 0, 1, 0. Keep going. If iter equals 3, open brackets, inside here we can just say at CD equals set 0, 0, 1. And as you can see, we're giving each iteration a different color. So every time this runs, we'll end up with a different color attribute. If iter equals 4, then we can give this a color of equals at cd equals set. We'll give this one a 1, 1, 0. And if you weren't sure, that's an RGB value of 1, 1. So R of 1, G of 1, that actually gives you yellow. It's a bit strange, but that's how it works. So last one, we'll say at iter equals 5. And let's make this last one orange. To make something orange, we can say at cd equals set. And orange has red in it, and it has some yellow. But we don't actually have a yellow, we have R, G, and B, so we actually put a 0.25 in place of our green value, and then 0. So close that off, we can apply and accept this. So you won't notice anything different yet. But if you go over here to our block end, you can see that each face has a different color. We have a red side, a green side, a blue side, an orange side, and a yellow side. And the reason that this happens is because as this goes over each iteration, think of it like this. A face is being passed into here, one of the faces from our bounding box. We're collecting the current iteration, so say the current iteration is 0. If the current iteration is 0, then we set our color to white. And then it moves on and it adds an iteration. So now we're on iteration 2. And then it will repeat that for each face. And each face gets a different color because each face is based on a different iteration. So the next thing that we can do is drop down a transform node. We'll plug this for each begin into this transform node and then scale this down by 0.95. We'll merge this back in. So beneath your attribute wrangle, merge your transform back in. Now we end up with this, these two planes, one beneath the other. And what we'll be doing is we'll be using this inside face to color the inside parts of our cube. So we can drop down a color node, plug that in between our merge node and our transform, and just set this to black. So now we have two cubes, one inside of the other, and you can't really see it here. You might be able to see it in wireframe. Quite difficult to see if you have the dark setting, but you can see a line there. So there's two boxes, one inside of the other. So that's great, because what we can do with that is transfer this attribute onto our cube. So just drag this up here, and then what we can do is promote. So we'll drop down a promote, attribute promote. We'll plug our for each into this, and in here we have the CD attribute on our points, but we would actually like it to be on our primitives. So change the class from point to primitive, and just select the name up there, CD. And now we can transfer our attributes. So drop down an attribute transfer. The first input will plug in our copy to points. Our second input will plug in our attribute promote. And the attribute that we'll be promoting is our CD attribute. And that will be on primitives, sorry. And we can go over here, change the distance threshold to 1. And now you can see that our cube has outside faces that are each of the corresponding colors, and the inside is black. It's a little bit difficult to show, but the inside is black, and you can see it by the edges over here. So now that we have a cube, we should probably do something with this. The next thing that we're going to be doing is dropping down an attribute wrangle. And my apologies for this, but this really is just menial labor once again. And so we're going to be doing a lot of typing for this one. I'm going to say if at p.y, which is our y position, greater than or equal to at y max, then do the following. And what we'll be doing is setting its point group. So we'll say set point group 0, that's our first input, comma, give it a name, so we'll call this one top, comma, at ptnum, the point that we want processed, and then 1 or 0 if we want it in the group, or 0 if we want it out of the group. So we want it in the group, give it a 1. Close that off. And so what this has done is it's taken that at y max value that we created earlier in this other attribute wrangle. And if you remember correctly, it's 0.25 because we have a cube size of 1 on the y-axis divided by 4. So 0.25, we're using that value as at y max. So we're saying if the current point's position in the y-axis is greater than 0.25, then assign it to a group and call that group top. What should happen is any points above 0.25 in the y-axis, they should be added to a group called top. So to test that, we can drop down a delete node, change its entity to points, then select our top group, and it should, there we go, disappear. So as you can now see, we have this top group. Now with that top group, we can do a couple of things. We can spin it on its axis and then reassign it. But we want a group for every side. So at p.y less than or equal to negative at y max, set the point group. Set point group 0, comma, bot, comma, at ptnum, comma, 1. And what I'll be doing is actually adding all of this to our blog post so that you can just copy and paste, because really you just need to do this 1 or 2 times and you'll get the gist of it. So now we can do at p.x greater than or equal to at xmax, put it in a group, set point group 0, comma, give it a name, call it right, right, comma at ptnum, comma 1, close that off. If at p.x less than or equal to negative at x max, do the following, set point group 0, comma, left at ptnum, comma 1. And so as you can see, what we're doing is we're taking the upper value, so at y max, the highest y value, and making it the top group. And then we're saying the point beneath the 0 axis, so negative 0.25, give that the bot group. And then we're doing the same thing over here. We're saying at the most x position, the x-most position, I guess, give it a right group. And at the least x position, give it a left group. So we'll just do this for the front and back as well, at p.z greater than or equal to at z max. Oh, I made a mistake over here. Group. Set point group 0, comma, front, comma, at ptnum, comma 1. And then we'll do this for the back group. So if at p.z less than or equal to negative at z max, do the following, set point group 0, comma, back, comma, at ptnum, comma 1, close, apply, accept. And if we drop a delete, we can try deleting each one of those. So let's try front, front disappears, try back, back disappears. Let's try bottom, bottom disappears. And so it seems as if all of them are working. Left disappears, right disappears. Great. So now we can begin using these groups to actually drive movement in this cube. So that's what we'll be doing in a solver. So the thing with using a solver is that when it runs, it'll do everything in the solver every single frame. Now that's good if you want a progressive effect. but it's not good if you want values to only be initialized at the start. So we have to initialize a few values that we'll be using first. We'll create another attribute wrangle, and in this one, we'll create our own variable called iteration, and we'll set it to equal 1. We'll go and create a rotation attribute, at rotation. Once again, this one will be set into 0. The last one that we'll create is an at pause attribute, and this one will equal 1. So these three attributes will all be used in our solver. This iteration we'll be using to count how many times our cube is being turned. Our rotation will count how much of a rotation it has, and then we'll use this pause to take pauses in between each rotation of our cube. So next, we can drop down our solver. And this is where all of the magic happens. Inside here, we'll be doing a bunch of things to this cube. So dive inside of the solver, and here's where the complicated wrangles come in. So bring up your editor again. To start this wrangle, we'll create a random variable. We'll call it float side. And what this will do is generate a random number between 1 and 6, 0 and 6, which will correspond to a different side of our cube. Say we get a value of 4, maybe that corresponds to the right-hand side, then we'll say flip that side. So this is just a variable that decides which side we want to flip. We'll say float side round to int. Round to int just rounds a value to its nearest whole number. So if you have 0.1, it'll round to 0. If you have 5.8, it'll round to 6. So we'll say round to int our random number. Let's generate a random number based on our iteration. So the iteration we created earlier outside of our solver was set to 0 or 1. Doesn't really matter. It's basically the seed for our random value. So multiply that by a random number. We'll say 1, 2, 3. Outside of the brackets, multiply that by 6 because we have 6 sides. And then we can close that off. Apply and accept. So now we have a random value between 0 and 6. The next thing we'll do is create a string called s@group. Won't initialize it to anything. We'll also create a direction to turn our cube, so v@dir for direction. Then we can go and say if side. Once again, it's going to be some menial labor. Apologies again, you can copy this from our blog, I'll make sure of that. Side equals 0. Then say that our string group equals top. And our direction equals curly braces 0, 1, 0. So a quick explanation of what's happening here. We're saying if this variable, right, that we've created called side, which is a random variable anywhere between 0 and 6, equals 0, then we'll set this group, this string group, to the group called top, right, which we created earlier. And the direction, so this is the direction that we'll be rotating around. Now, if you think about it, the top axis, or the top part of the cube, would rotate around the y-axis. It rotates relative to the y-axis. So we have to say 0, 1, 0, because we're saying which axis is this relative to. So we have it relative to the y-axis. So we can continue and do this for the rest of the sides. So side equals 1. Do the following. At group equals bot. And again, at dir, that'll be the same. We'll say 0, 1, 0. Because the bottom of the cube is the same as the top of the cube, it rotates around the y-axis. Again, we'll say if side equals, this time we'll say 2. Then do the following. And what we'd like to do is say at group equals right. Close that off. Say at direction. So let's think about this again in curly braces. What direction does the right rotate around? Well, the right would rotate around the axis that runs through it. And that axis would be your x-axis. So 1, 0, 0. You do if side equals 3. then @group equals left. And of course, that's the same as right. So direction would equal 1, 0, 0. We can say if side equals 4, then do the following. So what would we like to do? Say @group equals front. And once again, think about which axis would that rotate around. And so the direction that would rotate around is the z-axis. So we say 0, 0, 1. And then for our last side, we'll say if side equals 5 @group equals back. And say @dir equals the same as before, 0, 0, 1. And then after that, apply and accept. Of course, every single time our iteration value will provide us with a seed. But we're not changing our iteration value yet, so we'll always end up with the same seed. So in our next wrangle, we'll be doing the rotation of the side that we've selected in here, and then we'll add to our iteration, so that the next time this runs, we end up with a different value. So this next attribute wrangle is the one that actually deals with rotation. So drop down a wrangle, Alt-E to bring this up. This wrangle really is actually the complicated one. So in here, we'll say float rot for rotation equals 90 divided by a channel float that we'll create. And the channel float that we'll create is called duration. So basically, it will give us a value depending on how slowly we want this to rotate. So the bigger the duration value, the smaller our rotation each frame. So the next thing that we can do is say if @pause equals 0 equals 0, then rotate it. So we haven't actually done anything with our pause value yet, but we'll get to that. But we're saying that if pause is not true, so we're not paused, then rotate your cube, or rotate aside. We'll say if in-point group. Now in-point group just returns a true or false. Is your current point in the group that we're looking for? So we'll say 0 for first input. s@group, because we created that before. And that's going to be a random group. It's either going to be top, bottom, left, right, front, or back. And then the point that we want to affect would be our pt num. So currently we have two if statements. We're saying if we're not paused, and if this point happens to be in the point group that we're checking, then do this. Matrix 3, we'll call this I for identity, equals ident, close bracket. So that makes an identity matrix, a matrix of 1s and 0s. And then we can say rotate. Rotate I, comma radians. So this will convert degrees to radians. So we'll say rot, that value we created earlier, comma v at dir. V at direction, we created that earlier in the previous wrangle, and that's just the direction to which you would like to rotate. So we're saying, take this identity matrix, apply this type of rotation to it, so this amount of rotation, which will be equal to 90 divided by our duration, and rotate it in this particular direction. So the direction is corresponding to the group, of course, so if it's the top group, it will rotate around the y-axis. Finally, we'll say @p times equals I. And what that does is it translates our p value by this I value. So we'll be rotating our position by the amount that this has decided to rotate by. Next, outside of your if in point group, we'll say @rotation plus equals rot. So once again, rotation is one of those things that we created earlier. We're saying take a full rotation, so that would equal 90, and then divide it by a duration, and then do it the number of times until it equals 90, and we'll get to that part a bit later. So over here, we're just checking how much it has rotated. So for every rotation, we'll add to this rotation value. And that seems a bit complicated, but we'll get to it all, and hopefully it'll make sense at the end. We say else. So of course this is the else for the pause if. We'll say at pause minus equals 1. So what that does is it says if our pause is 0, rotate. If our pause is not 0, then minus 1 for now. So eventually your pause will equal 0, and then you'll rotate. So the next thing to do is say if at rotation greater than 90 minus rot, do the following. And so what we're saying here is if this value has accumulated enough rotation, then we want some things to happen. And what we're doing here is we're saying if the side that we've been working with, the group, has rotated a full 90, then do some things. So what would you want it to do if a cube's side was rotated entirely? Well, what you would like to do is change your iteration so that we can work with another side next. So we'll say at iteration plus plus. So our iteration increments up. And we can say at rotation equals 0, because now it's done a full rotation. So of course this value needs to be set back to 0 so that we can work with it again later. And then we'll say at pause equals channel integer pause duration, pause underscore duration. So we'll be creating this integer and giving it a value. So if you have a pause duration of 5, then if you remember how we used it up here, we'll say that, okay, pause doesn't equal 0 yet, so we have to minus 1. So for 5 frames, it won't be doing anything. Your cube will just be stagnant. Then it'll do this, and once it's rotated to its rest position again, then it'll reinitialize your pause duration. So what we can do now is set a bunch of point groups. So we'll say set point group 0, comma, top, comma, at ptnum, comma, 0. And that's the important part. What we're doing is we're removing all of the groups, because what we've done is we've used them. So now they've changed, because if you rotate, say, your right side upwards, all of a sudden you've got points that were now on the front face, they are now at the top face. So obviously they're not in the same group anymore. So we have to remove all groups from these. So we'll say at point group 0, comma, whoops, 0, comma, bot, comma, at ptnum, comma, 0. And just do this for every group. Set point group 0, comma, to left this time, comma, at ptnum, comma, 0. Again, set point group 0, comma, right, and ptnum, comma, 0. Set point group 0, comma, front, comma, at ptnum, comma, 0. And then finally, set point group 0, comma, back, comma, at ptnum, comma, 0. So after all of that, you've removed all of your groups. But now what? So now we don't have groups, but we still need those groups. So what we have to do is we have to get those groups back. And to get those groups back, we'll just apply and accept this quickly. And we have an error, we'll get to that shortly. What we need to do is we need to copy this group assign. If you remember correctly, we did it in this attribute wrangle, where we assign groups based on position. So select all of this, pressing Ctrl A, we'll copy this, go back into this, and over here, we'll paste all of it. So we've pasted it after we've removed all of the groups, right? So you can see it here. And I think the one thing that we were missing was a comma over here. Okay, so now we've removed all of the groups because our cube has rotated, and then we're reassigning the groups based on the new positions that we have. So if we apply and accept this and jump up a level, before we jump up a level, we need to create our spare parameters. So we've created our spare parameters. So duration, let's do 15 frames, and we'll pause for 3 frames. So jump up, set your real-time toggle on, and play this. And now you can see that that's exactly what we wanted to happen. It's rotating, it's resetting, it's pausing for 3 frames, and then it's doing it again. And it'll go on indefinitely, and we can mess around with those values, like a duration of 5 with a pause of 1, so, you know, short, snappy rotations. And so there you have it. Your cube is mixing itself up. And that's great. Like, this is quite a complicated piece of code, so I'll actually be going over this in our blog, and it'll all be fully explained. It's just, it feels as if I can't get through all of it just by talking about it, so, you know, I'll type it all out for you. You can go read that. So we'll set a duration of 10. Pause duration, we'll make this 5. Yeah, that feels smooth. So the last thing to do to actually make this play back, because currently we have it solved and then it's unsolving itself, but that's not quite what we want. So we'll say time warp, firstly. And then over here, we can choose how many frames we want this to run for. So over here, choose a range. So we'll say we want this to run for 120 frames. Cool, so we set input range over there to 120. And then our output range needs to be the reverse of this. So we'll copy this parameter and we'll paste it over here. Paste relative references. And then we'll set the output range's second value to 1. So as you can see now, we have this cube that's already been shuffled. And if you play this, you'll notice that it's now solving itself. And the reason for that is because it's playing in reverse now. And it ends at exactly 120 frames, because that's the range that you've given it. So if you give this a range of 500 frames, it'll automatically set your output range to 500 frames, and it'll play for 500 frames. And this is a really quick simulation to run, so you don't need to worry about running it for a lot of frames or even caching it out. And so that'll go on until 500. And so you can choose whatever range you want, and you can choose what speed you want. Perhaps you want this to do a lot of iterations with no pausing at all. You can play that back, and of course, you know, with 1 frame it doesn't even have a chance to spin. It's to a rotation of 2, duration of 2. Now it's just going crazy, but it works out, and it'll solve itself. And the last few things that we want to do is actually just give this a velocity to work with. And then we'll give it a poly bevel and a few other things to make it look more like a Rubik's Cube, because currently it kind of just resembles one, but, you know, not quite. So let's drop down a trail. This trail, we'll say compute velocity. And if we switch on our velocity trails over here, we'll play this back, you'll be able to see velocities being generated. So that's cool. We can use that to emit particles or for motion blur. And then we'll just drop down a poly bevel. This poly bevel will set its fixed distance to 0.015, a division of 4. We'll give it some corner faces and edge face output groups. And what that does is it just takes these edges over here and assigns them to a group. So now what we can do is we can say those over there, let's maybe just color them a different color. So color them black maybe. And it's actually a primitive group. So there we go. And now we can promote our attributes back up. So we can go back from primitive to point on our CD attribute. And we'll just use maximum. There we go. Now we have this cube that solves itself, generates velocities, has color. And in part 2, we'll be going over how to actually emit confetti from this, how to turn it into a rigid body. Basically just turn this into an object that becomes interesting, because there's nothing that great about this. It's just an interesting piece of Vex code. So I thought I'd share that with you. But in the next one we'll actually turn this into something fun. So thanks for watching.